Okay, chapter 13 is quantum physics and nuclear physics. The first portion is covering quantum physics and the second portion is covering an addition to the nuclear physics chapter that we did earlier. Now, quantum physics starts off with the photoelectric effect. So, you should basically be familiar with what happens in the photoelectric effect. There's a cathode ray tube, which is basically an evacuated or tube with vacuum inside, okay, and this tube is connected to two terminals, the negative terminal here and positive terminal. So the negative terminal is the cathode, positive terminal is anode. These two are metal plates, and what happens now, of course with this setup there will be no current flowing. There's an ammeter here, okay, but when light is shown on this surface here, it is observed that there's a current flowing. So current will flow in this direction, which means what happens now is there are electrons built up over here. When photons strike the metal surface, okay, photons strike the metal surface, they eject electrons on the surface, and these electrons then move from this part of the metal to the from the cathode to the anode. Okay, so Einstein had postulated that light exists in the form of photons in order to explain the observations from the photoelectric experiment. Okay, so I'm not going to go into the details of what was the exact history behind it, but basically you should know that photons will eject the photoelectrons. So these electrons are called photoelectrons. Now what happens is Einstein postulated that these photons have an energy equal to hf, where h is the Planck's constant and f is the frequency of the photon. So the energy, as opposed to being dependent on the intensity or amplitude, is actually dependent on the frequency of the photons. When this energy falls on the electrons, okay, part of the energy is absorbed by the metal as the work function. The work function is the minimum amount of energy required by a metal in order to eject photoelectrons. Okay, so that work function can be written as phi or hf naught, where f naught is called the threshold frequency. Okay, there's the minimum frequency that these photons must have in order to eject photoelectrons. The rest of the energy becomes the kinetic energy of the photons. Okay, but not all of the electrons. But not all electrons will have the same kinetic energy, but this here is the maximum possible kinetic energy of any electron. Okay. Now Ek max can also be written as over here we will write half me v max square. Okay. So this is the maximum kinetic energy of any electron that is ejected from this end. Okay. Now, of course, higher the frequency here, higher the amount of energy which is converted to the kinetic energy of the electrons. So, how do we measure this, and how do we determine that this is actually dependent on the frequency of the incident photons? What we'll do here is we will reverse the polarity of the battery, okay, so that there's an opposing force at this end. Okay, now so there is a negative terminal over here, and it's going to oppose the electrons flowing. So when we increase this the EMF over here, there will be a voltage for which the electron with the maximum kinetic energy is also not able to reach this point. At that point, the current will become zero. Okay, and that voltage is called the stopping potential. Okay, at the stopping potential, the kinetic energy of the maximum, the electron with the maximum kinetic energy does not have enough energy to reach the opposite end of the tube. Okay, now, therefore, the amount of energy that the electron must possess is the charge multiplied by the potential difference. Okay, so therefore, this quantity here will become EVS. Okay, so Now from here we have an equation Vs Vs equals h over E f, just rearranging that equation, minus hf naught over E. Now if I were to draw a graph of Vs versus f, okay, I would see that this is in the form of y equals mx plus c. Okay, so the graph would look like this: Vs, and this is frequency. Now notice that h and E are both constants, so regardless of what metal we are using, the slope of the line will always be the same. Okay, and the x-intercept here will be f naught. Okay, below f naught, below the threshold frequency, there is no current generated. Okay, like we mentioned, below the threshold frequency, the photons will not be able to eject electrons, and therefore the current will become zero, or the stopping potential will be zero. There is no current, so there is no stopping potential. However, if we were to extrapolate this, this would fall at this point over here, which would be this value, or in other words, the threshold of the work function divided by E. So this value here is minus work function divided by E. Okay, so for another metal with a higher threshold frequency, the graph would be here with the same gradient. Okay, now these are some of the salient features of the photoelectric effect. You should explain what were the observations which were not explainable by the classical wave theory, and what Einstein had proposed in order to overcome those limitations. So that was stopping potential versus frequency. If I had to see how the stopping potential, or how the potential that is applied over here changes with the current. So if my potential here was the original way, like that, okay, this is a positive potential, the current would simply be whatever the current is initially. Now that current is of course dependent on the intensity of the light, because higher the intensity, this means greater the number of photons, okay, therefore greater the current. Okay, this here is intensity. So a higher intensity would lead to a higher current, simply because there will be more photons, and more photons means more electrons ejected, and more electrons means a higher current. So for a given intensity, this here for a positive voltage would be the same current throughout, right? Current and voltage. But as soon as I reverse the polarity and try and stop the current would suddenly fall to zero at the stopping potential here. Okay. Now let's say my intensity was higher. When the polarity is positive, there would be a higher current. But when I again reverse the polarity, the current would slowly fall again, and it would fall back to the same stopping potential. This means that the stopping potential, or the kinetic energy of the electrons, is independent of the intensity. So the intensity is not affecting the energy of the electrons, but in fact the stopping potential is being affected by the frequency of the incident photons. So that is one thing that you need to make sure that the student understands. Of course, there is a graph of how the photocurrent varies with intensity. It would be directly proportional, of course. Greater the intensity, greater the current. Okay? And if there is zero intensity, there will be no current. But if the intensity is high, but below the threshold frequency, there would obviously be no current. Okay, so you need a high enough intensity and you also need it to be above the threshold frequency. So you can go step by step and explain how the photoelectric effect was understood and explained by Einstein using the postulates of the concept of a photon. Okay, 13.1.4 is just some problem solving using the photoelectric effect concepts. Now, next part is 13.1.5.